Good afternoon, all. Myself, Dr. Abhishek Tiwari. Today, I am going to give a talk on metallurgical thermodynamics. So, I will be covering two chapters: Thermodynamic Foundations and First Law of Thermodynamics. So, this is the outline of the presentation. In first chapter, I will be discussing about basic concepts and definitions of thermodynamic systems and thermodynamic variables and thermodynamic processes, cycle and equilibrium and reversible and irreversible processes, zeroth law of thermodynamics, and then I'll discuss first law of thermodynamics, in which I will be explaining about the internal energy, enthalpy, constant volume and constant pressure processes, isothermal and adiabatic processes, heat capacity, enthalpy of physical transformations and chemical reactions, then Hess's law and Kirchhoff's law, and applications and thermochemistry. So basically, what are the basic concepts and definitions of thermodynamic systems? So first, we try to understand what is thermodynamics. It is the subject which deals with relation between heat and motion. So thermo means heat and dynamics means motion. So it is the subject which deals with the relation between heat and motion, and development of metallurgical thermodynamics occurs due to application of chemical thermodynamics to the metal and materials, which later on known as thermodynamics of materials. Because it gives the idea about the feasibility of the process, end product, and its stability, and calculation of heat values. So let us consider a reaction A plus B giving you C plus D. So initially, let's say A plus B is at this level of energy, and C plus D is at this level of energy as shown in this figure. And so we have plotted free energy versus reaction coordinate, and when reaction is occurring from A plus B state to C plus D state, there is an intermediate stage, or in which activation energy is required for a reaction to occur. So to understand this, let us say we have this box, and if we consider if we consider if we consider the center of mass of this box as the energy level, and so let us say this is the unstable state, and this is the most stable state. So if the center of mass is here, and the intermediate, when it moves from here to here, the final state, in this intermediate state, this the center of mass will be higher than the initial center of mass. So we can say that extra energy, activation energy, is required for this reaction A plus B to form C plus D. Now, what are the definitions required to understand thermodynamics of metallurgical systems? So, what is system first? It is defined as any portion of the universe or quantity of matter that is chosen separately from rest of the universe and closed by a boundary surface. Now, what are the types of the systems? Depending on various types of various parameters, system can be classified as based on different things. First is nature of interaction. So how it is interacting with the surrounding. So first is open system. So if heat and mass transfer is possible, then it is known as open system. If only heat transfer is possible, then it is called closed system, and if neither heat nor mass transfer is possible, then it is called isolated system. Now, depending on the number of components also we can define the system. If system consists of only single component, then it is called unary component system. And if system consists of more than one component, then it is called multi-component system. Now, depending on the reactiveness also we can define the system. If system is chemically reactive, then it is called reactive system. If system is chemically non-reactive, then it is called non-reactive system. Now we can define based on phases present in the system, we can define whether it is single phase system. So we can call it as homogeneous system if there is only single phase present in the system. And if there are multiple phases present in the system, then it is called heterogeneous system. So as we can see in this figure, this is a system and it is separated by the surrounding from the surrounding by a boundary. And let's say there are two species in the system A and B, and so chemical interaction for species A can occur in the surrounding. Similarly, chemical interaction for species B can occur with the surrounding, and there could be thermal interaction. That means heat transfer is possible between system and surrounding. This is the boundary, and there could be mechanical interaction also. So, what is surrounding? Except the system, the rest of the universe is known as surrounding. What is boundary wall? So, this is in the figure you can see this is the boundary wall, and boundary wall can be of two types. One is adiabatic wall, and another is diathermic wall. What is adiabatic wall? If there is no flow of heat energy and matter with the system and surrounding, then it is called adiabatic wall. If the flow of heat energy occurs, but no flow of matter, means there is heat transfer, but there is no mass transfer, then it is called diathermic wall. Now, what are the thermodynamic variables? So, in metallurgical thermodynamics, we will have different thermodynamic parameters or state variables. So, there are two types. One is extensive parameter or extensive variable, another is intensive variable or intensive parameter. So what do we mean by intensive variable? Intensive variable when the parameter is independent of mass, then it is called intensive. So to remember, we can say independent means independent, intensive means independent of mass, and extensive, that is dependent of mass. So for example, extensive variables that are mass, area, volume, length, entropy, and enthalpy. Intensive variables which are independent of mass, for example, density is not dependent of mass. If we increase the volume, then it is not going to change. If we increase the size, then the density is not going to change. And specific volume, molar volume, so these are intensive variables. Now, thermodynamic processes, when two or more than two parameters get changed in a system, then it is known as thermodynamic process. So we can see different type of processes in this slide. First is cyclic process. So we can see here A to B to C to D to A. This is one cycle, and it is clockwise. So it is doing positive work because work is P delta V. So this is going in clockwise direction. So it is positive work. And if it is going from A to B to C to D to A in anti-clockwise manner, then it will be doing negative work, and it is coming from initial state A to final state A. So it is cyclic process. Okay. Now adiabatic process. In adiabatic process, delta Q is 0. So here we have this P versus V diagram, and this curve is represented by like this. So these are isotherms, and this green line is represented by adiabatic process, and the work done under this green line or this process, work done under this area, under this curve, work is represented by integration P delta V or PdV. Now isothermal process. So isothermal process. So as we know that PV equal to nRT. So T is constant. That means PV is constant. Now on y-axis we have P, and on x-axis we have V. So PV is constant. So this will be like xy is equal to c square hyperbola. So we can see here that it is represented by a hyperbolic curve. Now we have this isobaric process. So in this we have let's say PV equal to nRT. So isobaric means P is equal to constant. So V is directly, so P is constant. So PV equal to nRT. That means P is constant. So V is directly proportional to T. So here this P is represented as constant, and the area under this curve, when the process is occurring from A to B, then area is equal to P into delta V is equal to work. Now isochoric process. So in isochoric process, V is constant. So this is the initial state and this is the final state. And if we supply heat, then there will not be any work done, but this goes from initial state I to final state F. I will discuss the work done in these processes in the later slide. And now quasi-static process. So if this curve is continuous, then it is a quasi-static process. And if it is a discontinuous curve, then it is non-quasi-static process. Though it's the same process, but it is it is in discontinuous form. So quasi-static process is the process in which every small step is an equilibrium, so that the entire process is an equilibrium. And in thermodynamics, a quasi-static process is a thermodynamic process that happens slowly enough for the system to remain in internal equilibrium. And an example of this is quasi-static compression, where the volume of the system changes at a slow rate enough to allow the pressure to remain uniform and constant throughout the system. Now, cycle and equilibrium. So a thermodynamic cycle consists of a linked sequence of thermodynamic process that involve transfer of heat and work into and out of the system while varying pressure, temperature, and other state variables within the system, and that eventually return the system to its initial state. In the process of passing through a cycle, the working fluid system may convert heat from a warm source into useful work and dispose of the remaining heat to a cold sink, thereby acting as a heat engine. Conversely, cycle may be reversed and use the work to move heat from a cold source and transfer it to a warm sink, thereby acting as a heat pump. So you can see that when we are taking a heat from a cold source and moving it to sink that is at a higher temperature, it's not a spontaneous process. There is some work required for this process to occur, and that is done by heat pump. So at every point in the cycle, the system is in thermodynamic equilibrium, so the cycle is reversible, and its entropy change delta S is zero, as the entropy is a state function. A reversible process, a thermodynamic process is reversible if the process can return back in such a way that both the system and surrounding return to their original states with no other change anywhere else in the universe. It means both system and surrounding are returned to their initial states at the end of the reverse process. So if we are going from 1 to 2 to 3 and 3 to 4 and 4 to 1 and it's occurring in a reversible manner, then it's called reversible process. So there is an initial process of volume expansion and then restoring again back to its initial position. A process can only be reversible when there are no dissipative forces in the system and the process occurs in an infinitesimally small time. Now, irreversible process. An irreversible process is a thermodynamic process that departs from equilibrium in terms of pressure and volume. It occurs when the pressure of a system changes dramatically and instantaneously that the volume do not have time to reach the equilibrium. So it's a sudden process. So a classic example of an irreversible process is allowing certain volume of gas to release into volume, and by releasing the pressure on a sample and allowing it to occupy a larger space, the system and the surrounding are not in equilibrium during expansion process. So as we can see here, this is the initial process and this is the restoring process, but it occurs suddenly. You can see there is sudden expansion of the volume. Now question, so in which of the following process the system and surrounding do not come back to its original state after process is complete? So it's not in the reversible process, it's not in adiabatic process, it's not in quasi-static process, it's in spontaneous process. So correct answer is a spontaneous process. Now Zeroth law of thermodynamics. So Zeroth law of thermodynamics states that if two objects A and C are in thermal equilibrium with each other and separately object B and C are also in thermal equilibrium with each other, then object A and B are also in thermal equilibrium with each other. So we can observe that Zeroth law in a very common thermometer having mercury in a tube, and as the temperature is increased, this mercury expands, and since the area of the tube is constant, due to this expansion, the height is increased. Now, increase in the height of the mercury level shows the changes in temperature and basically helps us to measure the temperature. Similarly, another example of zeroth law of thermodynamics is when you have two glasses of water. One glass will have hot water, another having cold water. Now we leave them on the table for a few hours. Then the hot water will come to room temperature. Also, the cold water will also come to the room temperature. And they will be in thermal equilibrium with the temperature of the room after some time. Now, first law of thermodynamics. So it's very important. It says that change in internal energy of a system is equal to heat added to the system minus work done by the system. So basically, heat added to the system is utilized in changing its internal energy plus work done. For an infinitesimal change of state, du is equal to delta q minus delta w. Why we have represented u as du and q and w as delta q and delta w? It's because u is a state function and q and w are path functions. So u is represented by initial and final position and not by the path, but q and w, they are dependent on the path. So if the initial and final states are same, then integral of inexact differential may or may not be zero, but the integral of an exact differential is always zero. So cyclic integral of delta zero, delta w, or cyclic integral of delta q may or may not be zero. Also, the integration over a cycle for du will be equal to 0 as the initial and final state is the same. If no work is done on a thermally isolated closed system, then delta U is equal to 0. And this is one aspect of the law of conservation of energy and can be stated as internal energy of an isolated system remains constant. Now, internal energy, it is defined as the inbuilt energy that is responsible for existence of matter. It depends on the state variables or state parameters, pressure, temperature, volume, and number of moles. It is a state property, and since the state of internal energy is same as the state of dependent parameters, so it is known as single value function. Internal energy is the sum of energy associated with translational motion, vibrational motion, and electronic configuration. For a cyclic process, change in internal energy delta U is equal to 0 as the initial state and final state is 0. Uh, Initial state and final state is same. So the change in internal energy is 0. And internal energy is a perfect differential. So Ui will be represented as a function of pressure, volume, and temperature. Now, enthalpy. Enthalpy is defined as thermodynamic potential, which is represented by letter capital H, and that consists of internal energy U and product of P and V. So, H is equal to U plus PV. Now, if we are moving from state 1 to state 2, so at constant pressure, integration delta H from H1 to H2 will be equal to H2 minus H1 is equal to delta Q at constant pressure will be equal to, since it is U plus PV, so integration U1 to U2 delta U plus P integration V1 to V2 delta V. Here we can say it's at constant pressure, so P came out of the interval. Okay. So H2 minus H1 is equal to delta QP. Delta U from U1 to U2 will be calculated as U2 minus U1 plus P integration V1 to V2 delta V will be V2 minus V1. Okay. At constant volume process, integration H1 to H2 delta H will be equal to H2 minus H1 is equal to delta Q at constant volume will be equal to integration u1 to u2 delta u, and since it's p delta v, so p dv becomes 0 at constant volume. So h2 minus h1 will be equal to u2 minus u1. Now it states that the net temperature change throughout the process for isothermal process. We are discussing isothermal process. So for isothermal process, delta T will be equal to 0. And for reversible isothermal process, when ideal gas is moving from state 1 to state 2, then work done delta W will be integration of PdV from V1 to V2. So P, we can write nRT by V. Here N is M number of moles. So mRT by V into dV, and dx upon x integration is ln x. So here we can write W1 to 2 is equal to mRT ln of V2 by V1 is equal to mRT ln of P1 by P2. Here we have changed using PV equal to nRT equation, and the heat transfer involved in the process Q1 to 2 will be equal to mRT ln of V2 by V1 is equal to T delta S S2 minus S1. Why? Because the delta S is Q upon T. So Q will be equal to T into delta S. Now adiabatic process. So in adiabatic process, delta Q equal to 0, and it follows the following equation: PV raised to power gamma is equal to constant. So when the system is going from state 1 to state 2, then PV raised to power gamma will be equal to P1 V1 raised to power gamma equal to P2 V2 raised to power gamma is equal to constant. And from using ideal gas equation PV equal to nRT, we can convert this equation to T1 V1 raised to power gamma minus 1 is equal to T2 V2 raised to power gamma minus 1. And it can also be represented as P1 raised to power 1 minus gamma. T1 raised to power gamma is equal to P2 raised to power 1 minus gamma T2 raised to power gamma. And work done in reversible adiabatic process given by delta W will be equal to P2 V2 minus P1 V1 upon 1 minus gamma. This we can calculate using integration of PdV is equal to CV T2 minus T1. Now heat capacity. Heat capacity C is the quantity of heat required to raise the temperature of a substance by 1 degree, and C is equal to Q upon delta T. If the temperature change is made vanishingly small, then C is equal to delta Q upon dt. The heat capacity at constant volume CV is equal to delta Q upon dt at constant volume. So Q can be represented at U plus W. So du plus delta W upon dt. So at constant volume, delta W will be equal to 0. So CV can be represented as du upon dt at constant volume. And similarly, heat capacity at constant pressure. So Cp is equal to delta Q upon dt at constant pressure. So this can be represented as du plus Pdv plus Vdp upon dt at constant pressure, and at constant pressure this VdP term will be equal to 0. So this can be represented as dH upon dt at constant pressure, and Cp generally can be represented as At plus Vt square plus T raised to power Ct raised to power minus 1 plus D. Now, enthalpy of physical transformation and chemical reactions. The enthalpy change in a physical or chemical transformation is written as delta H and defined as H product minus H reactants. Because of this formalism, for exothermic reactions, we have delta H to be negative, and for endothermic reactions, delta S is positive. So in endothermic, delta H, we are providing heat, so delta H is positive, and an exothermic, heat is releasing, so that means delta H is negative. Now Hess's law and Kirchhoff's law and its application. So Hess's law states that the total change of heat in a chemical reaction is same irrespective of whether it occurs in a single step or in multiple steps, provided that the reaction must be isothermal or isobaric or isochoric. If a process occurs from A to B, then using Hess's law we can write as enthalpy change throughout the path AB is equal to sum of the enthalpies throughout AC, CD, and DB. So, so the reaction A to B can occur directly from A to B, or it can go through path A to C, C to D, and D to B. So delta H AB can be written as delta H AC plus delta H CD plus delta H DB. And now the Kirchhoff's law that states that if a system undergoes a change from one state to another state, then both internal energy and heat will alter. This means that integration of T1 to T2 d delta H is equal to integration T1 to T2 delta Cp reaction into dt. So delta Cp reaction can be written as delta sigma Cp product minus sigma Cp reactant into dt. So this can be represented as delta H2 minus delta H1 is equal to integration C1 to C2 sigma Cp product minus sigma Cp reactant into dt, and delta H2 is equal to delta H1 plus integration T1 to T2 sigma Cp product minus sigma Cp reactant into dt. Now we will talk about thermochemistry. So what is thermochemistry? It is the study of the heat effects accompanying chemical reaction and formation of solution and changes in the state of matter such as melting or vaporization and physical chemical processes. Now we will discuss some definitions which are important for discussing thermochemistry. First is the heat of reaction. It is defined as the heat evolved or absorbed when reactants react completely to produce products, and it is expressed per mole of reactant or per mole of products. Now heat of formation. It is defined as the heat evolved or absorbed when one mole of compound is found from its constituent elements, and it is expressed per mole of compound. It depends on the temperature and heat of formation of a compound out of its constituent element is called standard heat of formation when it is considered in standard state. Heat of combustion. So heat of combustion of a substance is the enthalpy change when one mole of substance is completely burnt in oxygen. So basically, if we burn one mole of the substance in oxygen, then the heat required for this reaction to occur is known as heat of combustion. And heat of solution, when one substance dissolves in another, there will be change in enthalpy, and that is known as heat of solution, and it depends on concentration of the solution. Now we will discuss one problem. Calculate the standard heat of formation of PbO from Pv and O2 at 227 degrees centigrade from the following data. Delta H 298 degree for PbO is given to be minus 52.4 kilocalorie per mole, and Cp of PbO is given to be 10.6 plus 4 into 10 raised to the minus 3 T Kelvin per degree per mole, and Cp of Pv is given to be 5.63 plus 2.33 into 10 raised to the minus 3 T calorie per degree per mole, and Cp of O2 is given as 7.16 plus 1 into 10 raised to the minus 3 T minus 0.4 into 10 raised to the 5 T raised to the minus 2 calorie per degree per mole. So we have this reaction Pv plus half O2 giving you PbO. So this is the heat of formation for PbO at 500 degree 500 Kelvin. So because 227 plus 273 will be equal to 500 Kelvin. So delta H 500 Kelvin for PVO will be equal to delta H 298 plus integration 298 to 500 delta Cp reaction into dt, as we have discussed in the previous slide, is equal to delta H 298 plus integration of 298 to 500 Cp PVO. Now this Cp reaction will be equal to Cp products minus Cp reactants. So Cp PVO minus Cp PV minus half of Cp O2 into dt. Now we put this equation, put these values from the given relations about Cp in terms of temperature, and we find that delta H 500 PVO comes out to be minus 51,998 calories. Thank you for your attention.